Okay, so this is part 3 of the videos on this particular problem. As you can see on the screen, the problem refers to the rolling of an inclined disc on the interior of a cylindrical tube. The inclined disc is mounted on a rod which initially passes through the axis of the cylinder, but then it bends. So as you can see here, this is the axis of the disc which bends from B, and so at A the axis connects with the disc. So the part BA is bent, and the disc is on the inside of this cylinder, and the way it is arranged and the way the length L and the radius R are is that the disc rolls on the internal side of the or internal surface of the cylinder. The question that we asked is to, and it is given that this vertical part of the rod is turning with a constant angular velocity capital omega, and the angle that this bent part makes is a constant beta. And in the problem we want to find out this angular velocity phi dot. This is phi dot as it is shown over here actually, and the question in this problem is to find the net angular velocity of the disc and to find the angular acceleration of the disc. So referring to this figure, which is enlarged over here, we can see that the point C is the contact point between the disc and the inner surface of the cylinder. The radius R and the length L are such that the point C is in contact with that inner surface of the cylinder, and it rolls without slipping. This is how the axis setup is given. In the problem, in the way we have solved the problem so far, we have considered at the beginning, when we started solving the problem, we took the XY/Z axis as per it is given in the problem. In the problem, the XYZ axis, which is the rotating frame here, this rotation axis is fixed to the bent part of the rod. Okay, however, it is not fixed to the disc. So it is fixed to the rod AB, but it is not fixed to the disc. As a result, this small x and the inertial z axis, they always form a vertical plane, and that plane contains this bent part of the rod. So we took this as our triad, as given in the, because this is given in the problem, and in the first attempt what we did is we in terms of the rotating frame, the rotating frame was fixed to the disc. So we have made this distinction that between rotating frame and the triad. We need to keep in mind that the rotating frame of reference is basically your reference in your mind as you are solving the problem, and based on that we identify or we formulate the velocity equations relating 2 points, and the triad on the other hand is basically used just to represent the vectors. So the triad is more of a mathematical artifact, whereas the reference frame, the rotating frame, is more of a conceptual idea that is used to formulate the relative velocity and relative acceleration equations. So this distinction is very important. So in the first attempt, our triad was as shown as and our rotating reference frame was fixed to the disc. In a variation of the first attempt, which we can call our second attempt, which is covered in part 2 of the videos on this problem, we have considered a case where the rotating reference frame is no longer fixed to the disc, but rather it is fixed to this rotating reference frame, which means essentially it is fixed to this bent part of the rod AB. So if your rotating reference frame is now fixed to this part AB, then there are certain differences in the formulation of the relative velocities between A and C, and you will see that in the second part of the set of videos we are making on this problem. All that is good, but now what we want to do is we want to extend this problem to a third part, and here what we'll do is we will now consider the rotating reference frame to be fixed to the disk. Okay, so going back to the first attempt, but our triad, now we are going to change the triad, which we did not do so in the first and the second parts, but now we are going to change the definition of the triad. Now we are going to say that our triad is also fixed to the disk. Okay, so it is still aligned, the z-axis of the triad will still be aligned along the bent part, but the x and y are going to be fixed to the disk. So as the disk turns, the x and y will turn with the disk. So essentially now it's going to be a body fixed reference frame where the body refers to the disk itself. So now we will show how to solve this problem where both the rotating reference as well as the triad are fixed to the disk. Okay, so that's the approach that we'll take, and hopefully this will give us a perspective on how problems like these in dynamics can be formulated in various ways, solved in various ways, and if you do so, it gives us a very good idea and it helps us distinguish between the rotating reference frame and the triad that we are using. So in order to proceed with this method, the first thing that we'll do is we'll make a sketch which will show how the triad is going to evolve over time. It's a little bit difficult in this case because of the fact that the disk is rolling without slipping inside of the cylinder, and so the diagram becomes a little bit tricky here, but we'll try our best. So let us assume that this vertical line still represents the vertical axis of the cylinder, and at a particular instant the disk looks like this. And this is the bent part of the axis L. So this point is B, this point is A, and our z-axis, the rotating z-axis, is going to go along the axis of the disk. Now unlike the previous case, so previously what we had assumed is that the x-axis goes like that, let's say. Now we are drawing kind of a perspective view, so let's say the y-axis goes like this. And so previously we have had a scenario where if I extend the x-axis, so this used to be x and this used to be y. If I extend the x-axis, it would always intersect with the axis of the cylinder. So previously the x-axis would always intersect with the, if you extended it, it intersected with the axis of the cylinder. And it formed between the x-axis and the axis of the cylinder, it would form a vertical line. A vertical plane. So we can say that this dashed, or this shaded rather, this shaded plane is a vertical plane. Okay. Now this is the angular velocity with which the bar AB is turning. Now as it turns and as this disk rolls without slipping on the inner side of the cylinder, what happens is that so over here the disk actually, as it rolls without slipping, it turns like this. Okay, as the hub AB turns this way, the disk turns like this. So if our small xyz, or the rotating, or our triad, is now fixed to the disk, then a general configuration of the triad is going to be like this, where x prime is here, y prime is here, this angle is phi, and so is this angle. This angle is beta. Now this is kind of an approximation, because if you imagine when the disk rotates, okay, on the and rotates without slipping, or rolls without slipping on the inner surface of the cylinder, this point A is also going in a circle. So really this rotation phi is also coupled with a motion of the point A, okay, in a circular path. But because of the complexity of such a diagram, we'll just show it this way, as if the point A is fixed. In reality it is not. And in our analysis we will take care of this by considering the right velocity of the point A. Now in this, so essentially our rotating frame is, so rotating triad is x prime, y prime, z prime, and the disk is turning in this manner as we have shown here. So this is phi dot. So that's the spinning of the disk. Okay, and we also make a note that our rotating frame of reference fixed to disk. So essentially I should say the rotating triad x prime, y prime, z prime and rotating frame of reference are fixed to the disk. So that's the setup of this problem, and we'll show how with this setup we can solve the problem. Now if initially there was this point C which was in contact with the inner surface of the cylinder, that point is now at C prime because X has turned and it's now oriented in the X prime direction, where X prime is the is at an angle of phi from the original location where C was in contact. Now our approach in this problem, in this approach, our approach is going to be to formulate Vc prime and set phi equal to 0 degrees, whereby or whereupon C prime coincides with C, and where Vc prime is equal to 0, since C prime is equal to C when phi equals 0. So that's the approach. So we are going to take the most general case and find the velocity vc prime as a function of phi, okay, and then we will set phi equal to 0. And when we set phi equal to 0, we can at that point say that at that configuration vc is equal to 0, and that is what will enable us to find out the angular velocity of the disk, and we will proceed with the angular acceleration vector as well. Now vc prime is equal to va plus omega d cross rho c prime with respect to a, right? We don't have the third term over here because our rotating frame of reference is fixed to the disk. Remember that if the rotating reference frame is fixed to a rigid body, then any 2 points that are on that same rigid body, they do not have any relative velocity in the rotating frame. So that is what is happening over here, and that is why we have just 2 terms in the velocity expression. Now let us formulate each of these vectors one by one. Okay, so the velocity of the point A is always going to be perpendicular to this shaded vertical plane. Okay, so and what is the direction that is perpendicular to this shaded plane? It is the y direction. So the velocity of A is always going to be in the y direction. However, note that the direction of rotation of AB is in this direction, which means that A is actually going into this vertical plane. So essentially the velocity of A is in this direction, which is exactly opposite of the y axis. Now keep in mind that this y is not y prime. Our ijk vectors are in the x prime, y prime, z prime directions. So we can say that VA is equal to, and if you go back to the earlier parts of this videos, you will see the formulation, but essentially it is negative L omega sine beta j. Now let us for clarity say that xyz corresponds to I, j, k unit vectors, okay, and x prime, y prime, z prime correspond to I prime, j prime and k prime unit vectors. It is also to be noted that z prime and z coincide at all times. Therefore, k prime and k are the same directions. Okay. So now the velocity of A is in the j direction and j is in this direction. Now we are working with a rotating triad which is along x prime, y prime, z prime. So we need to resolve this j, and you can see that j resolves to cosine phi j prime plus sine phi I prime. So okay, so that's our formulation for VA. Note that at this point we are not going to make any substitutions for phi. Once we have found out the overall velocity expression Vc prime, it is at that point when we make those substitutions. So we have we have VA. Now omega d, which is the disk's angular velocity, has two components. One is because of this phi dot, which is produced by the spinning of the disk, and the other is this constant capital omega, which is created by the rotation of the hub about the vertical axis. So we have essentially phi dot in the k prime direction. Note that k prime is same as k, and then we have capital omega in the inertial z-axis, which is so we need to do omega cosine beta, and that would produce a vector in this direction, which is in the negative k prime direction. Okay, the other vector is going to be produced in the x direction, which is omega sine beta. It is going to be produced in the x direction, and that x direction will have a cosine phi component in the x prime direction. So if I do cosine phi, that is going to be I prime, and it is going to have a minus sine phi component in the j direction. So minus omega sine beta sine phi j prime direction. So this is our VA, and this is our omega d. Next we have rho c prime with respect to A. Now since our triad is fixed to the disk, c prime with respect to A is Ri prime. Okay, so we now have all the three vectors. Now if we plug in these vectors into this equation, what we get is the following. We get Vc prime is equal to negative L omega sine beta cosine phi j prime minus L omega sine beta sine phi I prime, and then omega cross rho c prime with respect to A. So we will do k prime, and this is in the I prime direction. I am sorry, this is in the I prime direction, because c prime with respect to A is R in the I prime direction. So k prime cross R I prime is equal to j prime. So you would have plus R phi dot j prime, k prime again cross I prime is j prime, so minus omega sine beta j prime capital R, and then I prime cross I prime is equal to 0, and then j prime cross I prime is minus k prime. So we'll have plus capital R omega sine beta sine phi k prime. Okay, so at this point we can combine some of these terms. So we will have R phi dot minus R capital omega cosine beta minus L capital omega sine beta cosine phi j prime minus L capital omega sine beta sine phi I prime plus R capital omega sine beta sine phi k prime. So now this is the general expression for the velocity of c prime as the disk turns. We are interested in finding out what happens at phi equals 0, because we know that when phi is equal to 0, Vc is equal to 0. So we set phi equal to 0, which means that this will be 0, this will be 0, and this will be 1. So therefore, at phi equals 0, Vc prime is equal to Vc is equal to 0 is equal to r phi dot minus r capital omega cosine beta minus L capital omega sine beta j prime. And by the way, when phi is equal to 0 degrees, note that j prime becomes equal to j, right? So so this is true. So therefore, from here we can say that phi dot is equal to omega cosine beta plus L over capital R omega sine beta. And you can verify that this is exactly what we had in the first and second part, or the first and second approaches that we took to solve this problem. Let me just quickly check. Yep. So next, what we'll do is we'll derive the final expression of the angular velocity, and and you will be able to verify that indeed the angular velocity expression also matches with what we had in the first two approaches. And then we will go to finding the angular acceleration of the disk. So let me just keep this over here. So the angular velocity of the disk is, as you can see from here, phi dot minus capital omega cosine beta k prime plus capital omega sine beta cosine phi I prime minus capital omega sine beta sine phi j prime. Now we have the expression for phi dot. This expression for phi dot, however, is true at the situation where phi is equal to 0, and at that point the velocity of c is equal to, well, let me just check one thing. Alright, so we have found the expression for phi dot. This is the general expression for phi dot. This is true at any instance, because the value of phi dot was found out by imposing Vc is equal to 0, and that happens at phi equals 0 degrees. But the expression for phi dot that we found is the general expression for phi dot. Alright, it is just that substituting phi equals 0 enabled us to set Vc equals 0, which then gave us the value of phi dot. Okay, so we substitute for phi dot here. As you can see, phi dot also has in its expression a omega cosine beta. So phi dot minus omega cosine beta is nothing but L over R capital Omega sine beta. And I should put a k prime here, although k prime is again same as k. So this turns out to be L divided by R capital Omega sine beta k prime plus capital Omega sine beta cosine phi I prime minus capital Omega sine beta sine phi j prime. So that's the expression for omega d, the angular velocity of the disk, as a function of phi. So you can see that the angular velocity of the disk, the net angular velocity of the disk, is not constant. Okay, it's a function of phi. However, if we are interested to find out what the angular velocity is at phi equals 0, we can set phi equals 0 here, where sine phi will drop out and cosine phi is going to be equal to 1. So L over R capital Omega sine beta k prime plus capital Omega sine beta I prime becomes the expression when phi is equal to 0 degrees, which is the configuration at which the problem asks us to find out the angular velocity of the disk. So this is the when phi is equal to 0, that's the angular velocity of the disk, which means that if you take the angular velocity vector and resolve it in the I prime, j prime, k prime direction, then you will have a dependence on phi. Okay, so as the I prime, j prime, k prime vectors they turn, what you see is in terms of the vector components I prime, j prime and k prime, you see a variable angular velocity. But you can see here that the angular velocity magnitude is going to be constant, because this term square plus this term square is going to remove the the phi term because of sine square plus cosine square. So indeed the angular velocity of the disk is going to be a constant, but it is just that when you express it using I prime, j prime and k prime, which are fixed to the body, then you see the components along I prime, j prime to be a function of phi. So that is expected. Of course, we should say that when phi equals 0, this reduces to L over R sine beta, L over R capital Omega sine beta k plus capital Omega sine beta I. Okay, so we have our expressions for the angular velocity. Now let us go to find the angular acceleration. Now to find the angular acceleration, what we need to do is to take, if we take this approach, that is our I prime, j prime, k prime are fixed to the disk, then what we need to do is we need to take the derivative of this vector and consider I prime, j prime, k prime rotating with the angular velocity of the disk, because I prime, j prime, k prime are now fixed to the disk. So if we take the derivative, we will have capital L over R sine beta k prime dot plus capital Omega sine beta cosine phi I prime dot minus capital Omega sine beta sine phi dot I prime minus capital Omega sine beta sine phi j prime dot minus capital Omega sine beta cosine phi dot j prime. right? So that's the acceleration term. We have to be very careful over here that we don't, when we take the acceleration, when we find the acceleration, we should not work with this one, because this is a very specific velocity term. So if we differentiated this, we would get an incorrect answer. We should take this general vector representation in our current choice of I prime, j prime, k prime. So we take the most general expression, we differentiate this. Once the differentiation is done, at that point we can substitute phi equals 0. Because if we substitute phi equals 0 beforehand, then we wouldn't calculate the phi dots, and we have to keep in mind that the angle phi is changing. So that is why here it becomes very critical for us to work with the most general form of the angular velocity as expressed in the I prime, j prime, k prime coordinates. Now that we have taken the derivative, we are ready to substitute for phi to find the acceleration when phi is equal to when phi is equal to 0. So at phi equals 0 degrees AD, then if we need to find it out, what we'll have to do is we'll have to set this to 0, we'll have to set this to 0, we'll have to set this to 1, and we'll have to set this to 1. So essentially the expression becomes L over capital R, capital omega sine beta, k prime dot plus capital omega sine beta I prime dot. This term drops, minus capital omega sine beta phi dot j prime. So as you can see, we need to find the time derivatives of j prime and k prime. So we note that k prime dot is omega d cross k prime, and I prime dot is omega d times I prime. Why is that so? Because by definition, when we take the derivative of a vector, we need to consider the angular velocity of that unit vector. Okay, so when we take the derivative of a unit vector, we need to consider the angular velocity of that unit vector, the absolute angular velocity of that unit vector. In this case, the absolute angular velocity of the unit vectors I prime, j prime, k prime is omega d, because our I prime, j prime, k prime are fixed to the disk. So therefore AD, the acceleration of the disk at phi equals 0, note that we don't have to take any other derivatives, and therefore we were good to set these phis to 0. If we had to take derivatives, any further derivatives, then it wouldn't be a good idea to set these derivatives equal to, or rather these terms equal to 0 and 1 at this point. So we have L over R, capital omega sine beta, and now let's do k prime dot. So k prime dot is omega d cross k prime. So k prime cross k prime is going to be 0. I prime cross k prime is going to be minus j prime. So we'll have minus omega, capital omega sine beta cosine phi j prime. Then we will have j prime cross I prime, which is going to be j prime cross k prime, j prime cross k prime, which is going to be I prime. So it's going to be minus capital omega sine beta sine phi I prime. Now another thing to keep in mind is when we are carrying out the cross product, these cross products, note that we are using the most general form of the angular velocity. Again, very critical. we don't want to make substitutions before we put in the most general form of the formulation. In fact, you could be a little bit more cautious when you go through this part and say that I'm not going to put phi equals 0 degrees at this point. I put it just because I knew that by putting them at this point will not cause any loss of generality. But when in doubt, you should not make those substitutions until you have derived the final expression. Of course, if I did not make those substitutions there, the final expression would also have been quite a bit more cumbersome. So this is also in the interest of time. Alright, so this is the first expression. Then we have plus omega sine beta, and we'll have to do I prime dot, which is omega cross I prime. So k cross I prime is going to be, k cross I is j, so capital L over R capital omega sine beta j prime. Okay, k cross, so I cross I prime is 0, j cross I prime is going to be minus k, so minus omega sine beta sine phi k prime. So this was j cross I, and so k prime, because and this negative becomes a positive. Okay, and then finally we have minus omega sine beta, and we can substitute for phi dot. Phi dot is omega cosine beta plus L over R capital omega sine beta, and this is going to be in the j prime direction. Okay, so then at this point now we can make the substitutions for phi equals 0. So this drops out, this drops out, this becomes 1. So we have made the substitutions. So one thing that we can see is that the I prime component and the k prime component have dropped out. So what we are left with is the following terms: minus L over R capital omega squared sine squared beta. This has dropped, plus L over R omega squared sine squared beta. Okay, and then another L over R omega squared sine squared beta, and a negative omega squared sine beta cosine beta, everything in the j prime direction. By the way, this is equal to j when phi is equal to 0 degrees. So we could write this as j because we have substituted phi equals 0. So we cancel these two, and what we are left with is the following: minus omega squared L over R sine squared beta plus sine beta cosine beta, and we could put j or j prime. So this is our expression for the acceleration of the disk. Okay, and you can verify that if this is indeed the expression that we got with our prior methods, which validates this method. So this brings us to the end of this video. What we have done here is we have taken an alternate, in fact a third approach to solve our problem, where we have deliberately chosen our triad to be fixed to the disk, and our rotating reference frame was also fixed to the disk. As a result of our triad being fixed to the disk, we had to be careful about considering the most general configuration of the triad in expressing our vectors. We had to be careful about calculating the time derivative of those rotating unit vectors, and also we had to consciously allow the time derivative of the angle phi, because clearly that's not a constant. And so we had to, because phi appeared in our formulations, we could not substitute phi equals 0 randomly. Rather, the approach is to solve for the overall expression for angular velocity or angular accelerations, and then substitute phi equals 0 or any specific value that you may have. So that is another thing to keep in mind when you are working with unit vectors or position vectors. We need to express, before we differentiate, we need to express them in the most general form. So that's it. Thank you so much.